Welcome to this lecture on the Digital Signature Standard or DSS. In this session, we will explore how data secures digital communication by providing authentication, integrity, and non-repudiation. DSS is a standardized approach to digital signatures. It is designed to verify that a message or document has not been tampered with and was sent by the claimed sender. So these are the key components of digital signature standard. These components from the backbone of DSS, they enable secure key generation and signature creation, which are crucial for digital security. We are taking a large prime number. The prime number P we are taking, and this is a prime divisor of P minus 1, which is nothing but the subprime Q. This prime is typically 160 bits of hash SHA1 or SHA1, and we are taking one generator. The number G we are calculating as G is equal to H power P minus 1 by Q mod P, where H is any number less than P such that G should be greater than 1. And we are taking the private key. The private key is kept secret by the user, which is nothing but the X. We are taking a randomly selected integer here X, where 0 less than X less than Q. We are taking a public key which is derived from the private key. The public key is Y. We are taking Y is equal to G power X mod P. And we are taking the hash function. The hash function, secure hash function, we are taking SSA1 or SSA26, which is used to create a digest of the message. So how DSA works? This is the key generation. We are taking two parameters here, P, Q and G. So these are the chosen parameters P, Q and G. We are taking one private key X, which is randomly chosen, which is 0 less than X less than Q. We are computing the public key Y. Y is equal to G power X mod P. And we are distributing the P, Q, G and Y as a public information, and only X we will keep it secret. In the signature generation, random ephemeral key we are using, that is K. We can compute the hash message H is equal to hash of M. We will choose a random integer K, where 0 less than K less than Q. This is used unique for every signature, and we are computing R is equal to G power K mod P of mod Q. And we are computing S is equal to K inverse of H plus XOR of mod Q. For signature verification, this is a signature page, we are taking R comma X. Now for the signature verification, we are verifying P is equal to GU1 into YU2 mod P of M. So here we are checking to verify a signature R comma S for a message M. We will check that the R should be less than 0 and Q, and S should be less than 0, and in between S0 to Q, R should be in between 0 to Q. If not, the signature is invalid. We are computing the hash message H is equal to hash of M. We are computing the W is equal to S inverse mod Q, which is the modular inverse of S. We are computing these two U1 and U2 value. U1 HW mod Q, U2 RW mod Q. So this is the signature verification. We will compute V value, which is equal to G power U1 into Y power U2 mod P of mod Q. We are verifying if V is equal to R, the signature is valid. If it is otherwise, it is invalid. So this DSS involves mainly 3 steps: key generation, signature creation and verification. Each step is mathematically designed to ensure authenticity and prevent forgery. For example, suppose we have a hash of a message using the private key and a randomly chosen value k. We compute R and S as part of the signature. This signature is unique and tied to the message. So these are the applications of DSS which we can provide authenticity and integrity. Authenticity means ensure the message is from the claimed sender and has not been altered. Authenticity means which we can keep it secret. Authorized integrity means which cannot be altered. Non-repudiation means the sender cannot deny generating the signature. Here we are providing the secure communication by using the protocols like SSL or TLS and PKY. Secure socket layer, transport layer security, and public key infrastructure. By using these protocols, we are securing the communication. So these are the advantages here we have. In advantages, DSS offers a reliable way to ensure secure communication backed by robust mathematical principles and global standardizations. So these are the limitations here we have. The limitations are, these are the computationally intensive compared to symmetric cryptography. It can rely on the strength of hash functions. For example, SHA-1 and SHA-256 algorithms. To summarize, DSS is essential for secure digital interactions, ensuring data authenticity and integrity. It is a cornerstone of modern cryptographic systems. Let us implement the digital signature standard algorithm. Here we are using the header files stdio.h, lib.h, math.h, and time.h. stdio.h, which provides input-output functions like printf and scanf. In stdlib.functions, this includes functions for random number generation and memory management. Math.h, which provides mathematical functions like power, POW, and time.h, which is used for generating random numbers seeded with the current time. So this is a function to compute modular exponentiation. So this efficiently calculates base expressions. This base percentile mod ensures the base is within the modulus range. Initially, exponent percentile mod 2 is equal to 1. It checks if the exponent is odd, it has to be multiplied with the results. Expression is equal to expression which can be right shifted towards 1. This divides the exponents by 2, right shift. It returns the final modular exponentiation value. In modular inverse function, this finds modular inverse of a modulo m, an integer x such that a into x percentile m is equal to 1. This returns modulo inverse or 0 if it doesn't exist. Coming to the main function, P is the prime modulus, Q is the subprime divisor of P minus 1, and G is the generator value for DSS. Coming to the private key, here X is a private key, Y is a public key, K is random ephemeral, K is the random ephemeral key value. R comma X signature key components, R comma S are the signature components. Here we have H is the hash value of the message. W, V, U1, U2, these are the intermediate values for verification. Let us assign in the DSS parameters. Here we have hard-coded DSS. So the parameters we are taking, P is equal to 23, Q is equal to 23, P is equal to 23 and Q is equal to 11 and G is equal to 4. Here we are computing the private values and public values. So here we can prompt the user to enter the hash H value. We can generate the random k value here. So we can displace the computer signature components of R and S. So this is the verification process we are taking here. In the verification process, if V is equal to R, then the signature is a valid signature, otherwise it is an invalid. It can return 0, it ends the program successful. Let's run the program here. Equal to 23. So this is our private key which is kept secret, that is 6. The public key we are taking 2. We are taking the hash of the message h is equal to 7. Then the signature R is equal to 9. That means the signature generation and verification will be done here. 9 and 9. The verification process is completed. Both are equal number here we have. So the signature is verified and the signature is a valid signature. If the values are different, R comma S, then the signature is invalid. With this, we are concluded our session. Thanks for watching.